which I think is really cool. So without further ado, here is Drew.
Thank you, Byron. I appreciate the introduction, and I have to say I've really enjoyed working with Byron recently. Last several years, he's been a key collaborator. Let's see. So I guess I want to first say good afternoon, and I wanted to say how exciting it is to give a talk at the very first conference on robot learning. That's a super cool opportunity, and tell everyone to reach out and thank the committee for making this happen. I think surely they were surprised by the reception and the fact that we unfortunately can't even fit everyone who wants to come in. So clearly the time was right to make this kind of event happen. It's very exciting. As Byron said, I spend a lot of time these days thinking about self-driving cars and the interaction of self-driving cars in the environment, and I'll allude to that in a minute. But the overall thesis of my talk is that it's very profitable for us as roboticists to think about the game theoretic aspects of machine learning. Kind of in contrast with traditional statistical learning where there isn't necessarily a game theoretic aspect. And so what I'm going to do is take you through a few examples of where I think game theory arises, both in applications, but also in the sort of fundamental development of algorithms, and see how maybe that viewpoint can help us. So as I mentioned, there's lots of interesting applications in self-driving cars. Getting a car to drive by itself with no one else on the road is not as challenging. It's definitely a challenge. But the real interest comes when you start interacting with the other agents, when it's fundamentally a multi-agent problem. We act with the other drivers on the road, we interact with the pedestrians, so on and so forth, and also the correlating devices, things like a traffic signal that tell us what to do. This kind of game theoretic aspect is what really makes the problem hard at some level. My own personal opinion is that machine learning is the key to delivering this technology. And it's the key in kind of both the traditional view of perception, and I'm showing here some work on single image detection of vehicles in 3D, detection and estimation, but actually not just in perception. I think it plays a critical role in forecasting the intents of other agents. It plays a critical role in planning and decision making, and ultimately in control. So my personal view is that it's going to go up and down the entire stack. But we're learning in a game theoretic environment. There's always other agents. Things we learn affect the behavior of a robot. That in turn affects the response of other actors in the environment. And one of my students, Arun, showed me this video. And there's lots of videos like this that you can find on the web, which just shows you how game theoretic urban driving can be. What's amazing is people are able to interact with all the other folks in this environment and make progress. And despite the fact that there are a remarkable number of accidents at a given time, people are actually surprisingly good at this task. It's really quite amazing. Yeah, it is quite something, isn't it? So again, I think the overall point I want to make in this talk is that learning in game theoretic settings is everywhere. And that was just one example, albeit one particularly exciting example. And now I want to give you a couple others where they come up, starting first with some other applications. So one of the projects that I enjoyed working on the most was collaborative work with the University of Pittsburgh, and particularly Andy Schwartz and Jennifer Collinger. And the work they've done, and I'm just setting up their work here, is truly amazing. So what they did is they took a cortical implant, so an implant that's put in the motor cortex, and actually measures neural spike trains. They built a decoder. For the sake of this discussion, think of the decoder as basically linear regression from neural spike trains that come in to the position that a person intends their hand, their end effector, to be at in space, either position or velocities, in 4 degrees of freedom. So X, Y, Z, and something which relates to grasping, right? So kind of how much they want to squeeze their hand together. And then take that decoding and send it off to a robot manipulator, right? And with this technology, they were able to take a tetraplegic subject, in fact, multiple ones, and have them be able to do tasks like pick objects up. And I encourage you, there's a CBS 60 Minutes on this, on some of their early work, which I would have included a little bit, but I'm afraid I would have run out of time. It's well worth watching, and the technology is quite amazing. And they've gone well above and beyond that now. Their work is very interesting. It turns out, however, there are some substantial challenges in neural prosthetics. And I'm showing a few examples here. So one problem is degradation over time of the signal quality of the neural implant. It gets worse over time due to the physiology of the brain. This inter-day changes in the recorded units. As I said, I find it amazing that the brain actually encodes this kind of 4D position of end effector directly enough that you can extract it. It's kind of amazing. But that's still a limited set of degrees of freedom that can be extracted. In particular, things that you can't extract or that we don't know how to extract are intended forces, right? And so much of our interaction in the world is inherently forceful. If you want to open a door, you have to think about compliant motion with the door. There's no ability to do that. Synchronization of hand and arm movements is quite difficult. And what you'll find, and I'll show you examples later, is the coarse motion of the arm is actually quite good. Fine motor skills to pick things up is actually quite difficult for the person using this technique, particularly as the signals degrade over time. So we developed a system that we called Arm Assist, which is autonomous robot manipulator assistance. And the way the system worked, and this is in collaboration with the folks down below, including Katarina Muehling, Arun Venkataraman, Shervin Jagdani, and Jean-Sébastien Valois. Arun is somewhere around here presenting his work. You could look at multiple inputs to this system. So a brain-computer interface, like the neural decoder I just described, but also a 3D joystick, or even a GUI on a computer, as potential sources of information that are giving you these 4D coordinates. And then we looked at combining perceptual information, so computer vision and force torque sensors, position, so on and so forth. Taking advantage of all this information to build up a model of what was in the world, and then inferring from the person's partial motions what their intents were. What were they actually trying to accomplish? Were they trying to pick up an object? Were they trying to open a door? What was their goals? Given the probabilistic soft inference of their intents, we then used a technique called hindsight optimization to try to figure out a policy that would improve the person's performance, but in a subtle way. So try to accomplish the task they're doing, but in a way that they would barely notice. That was kind of the overall goal. And this is the system we built. The machine learning component of this is really in the intent inference, although there's also a learning component, in a sense, in the planning part. And then ultimately controlling an arm. And so I'll take you through this very quickly in a little video. So the very first thing is goal prediction, figuring out what people are trying to accomplish. And so what I'm showing you here, and I'll play it again, is this is actually not simulation. It looks like simulation, but it's the robot's mental model of what the world looks like. And you'll see the real world in the mental model in a second, right? But the person's actually controlling this, and this is how the robot thinks the world is. So it thinks those are the potential objects in the world. Given the motion of the arm that the person is commanding, what are they actually trying to accomplish? Which objects are they trying to grasp, and how? Okay, and so you'll see that shift as the person moves the arm around. So there's no assistance going on, the person's just making the commands themselves. Okay. Given these inferences of what the person is likely to do, what you see now is a value function, a sort of 2D version of a value function, even though it exists in the full dimensions of the robot, which is how good is it to move the robot arm in that direction to help them accomplish some task. And so now you're seeing both the kind of robot's eye view as it's tracking its own arm and tracking the other objects in the scene. And the person is reaching out, and the robot is now actually helping them to accomplish tasks. And the person is only entering X, Y, Z, and again, a one-dimensional command to kind of squeeze. So then we applied this and applied it to a variety of tests which are used as tests of rehabilitation, particularly for stroke patients. So one of these is called ARAT, and another one is box and blocks. And what's going on is the person is trying to use this brain-controlled interface to actually pick up objects. And again, as I said, their coarse motions are actually quite good, and their fine motions are not great, right? And you'll see that. And the subject in this case is struggling to be able to pick up this box and move it onto that yellow pad, right? And you can see that. Now, to me, the most amazing part of this project, beyond the absolute magic that you can put an implant in someone's head and decode how they want to move their own arm and then turn that into motions of a robot arm, which I find amazing, is that we were able to set up the system that inferred intent and then subtly changed the commands that were being executed by the person in a way that the subject in a blind study could not actually tell whether or not the system was working, except that it roughly cut their time to accomplish tasks by about a factor of 3. So you would ask yourself, how is it possible that you could be 3 times faster and the person wouldn't be able to tell? Well, there's a lot of variability in the subject's ability to use the system, and some days they have good days. So if it was a blind test, they just thought it must be a good day, right? They didn't actually realize they were getting assistance, which to me is the perfect way to apply this. It's helping them accomplish something, and they don't even know that, that it's fighting them, for instance. Okay. So the key to that is a kind of soft inference procedure. So this is the subject trying to open a door earlier, and then we applied the same system where it's inferred that the person's trying to grab the handle and what forces are required to hold the handle, grab the handle, and open the door. And so the subject was able to do things like open doors, pour cans of Coke, a variety of tasks that she described as some of the most exciting things she'd done since being able to control this. And the final version is we did a lot of work, particularly Abdeslam Boliaris did a lot of work on being able to manipulate items and clutter very effectively in an autonomous way. And then we combined that with this technology so that a person could figure out what they wanted to pick up and pick up any object in a cluttered environment, right? Whether those are natural objects or, in this case, just a pile of stuff lying around the lab. Okay. Some of my students, together with Sid Srinivasa's lab, did a bunch of work on extending this to other device interfaces, in particular modal interfaces. So one interface to robot prosthetics that's fairly common is you have something that's like a joystick, but you can only control some of the degrees of freedom of the arm at a time, right? Even though you have many degrees of freedom. And you might imagine it's actually quite hard to do a manipulation task when you're switching between these degrees of freedom. And we applied the same technique, the kind of key difference being the assistance was largely focused on the off modal. So whatever the person was not controlling, the assistance was helping in those off axes to try to accomplish the same tasks. What I'm going to show you in the next video is some work on a feeding task. Feeding is a particularly interesting task because it's very important. People view it as a very important thing that they be able to do themselves, and they want to be able to control exactly what bite they take and so on and so forth, but they want to be able to accomplish it. And so the 2 videos to watch are the bottom right. The bottom right is the direct modal control of the interface. And so what's going on there is the person is controlling, for instance, X, Y, and then they can switch and control another axis, and then they can switch and control angle axes. Okay? And the picture above is this hindsight optimization plus intent inference thing I was describing. So you're trying to figure out what the person is trying to accomplish, and then you're helping them, particularly in the off-modal axis, accomplish the task. I won't go into the details of the 2 other videos, but there are 2 other variants that don't work as well for various reasons. So watching the upper right, subject has decided that she's going to pick up that particular marshmallow, and in about 13 seconds has successfully gotten it. And that's interesting to watch her struggle to control with the modal interface to be able to grab the particular bite of food that she wants to grab. And we are well over double the amount of time, and you can see she's still struggling to be able to gain control. It's actually quite a hard interface to use if you've ever used one of these modal interfaces. I know it ends at 50-something seconds, so. There we go. Okay, we'll skip some of the other ones. So what's the point of all this? The point of all this is, well, one, I think shared autonomy is this kind of parallel shared autonomy is a really amazing research area and has very practical applications to improve people's lives. But beyond that, there's this problem we're looking at, which is simultaneous prediction and assistance. We're trying to predict what the person is doing and then assist them in doing that task in a non-intrusive way, right? And so the problem is, what goal are they trying to do? What task are they trying to accomplish? Okay. The interesting thing is the application of that assistance actually changes how users act, right? So as they learn, for instance, the system is able to control off-modal degrees of freedom, they may start, for instance, changing modes. right? And so now we're actually changing how we should infer what they're doing, right? So there's this interaction between what the robot does and what we should predict the person is trying to do, okay? And the overall summary of this is, because the learner responds to the user and the user also responds to the learner, it's best to think of this rather than, I described it kind of an optimal control setting, it's really better to think of it as a cooperative game where both the human and the robot are actually trying to accomplish the same task, right? So they're both trying to get the same thing done, and the robot just doesn't know exactly what that task is. Okay. When I showed you that previous example, the inference of intent that I described is based on a technique called inverse optimal control, which I'm going to talk about here, where you're trying to figure out, you're assuming the person is acting in a semi-optimal way, and you're trying to figure out what actually they're trying to accomplish. And that's how you're able to infer intents. And some of the first work I did on inverse optimal control was in outdoor mobile robots. And I'm just showing a few examples from this. And the problem here is actually quite simple. The problem is you have a big outdoor robot. You want to get a robot from point A to point B by itself. Your mental model is point A and point B are separated by maybe 1 to 10 kilometers. And you should think of the terrain, in this case it's kind of desert terrain, but as sort of arbitrary. It could be the woods of western Pennsylvania, or it could be the high desert of Washington. Okay? And what you need to accomplish this task when you have things that are distant from each other is you need deliberative, intelligent behavior that kind of stitches together long sequences of decisions. And the question is how you do that. It turns out to be fairly difficult, at least in my opinion, to program these robots to do what you want them to do manually. There's a lot of work to make that happen, and it's very hard. And in fact, interestingly, and that will come in a moment, the single most commonly touched piece of code in this particular code base was a system that did costing for the robot. So that took the output of all the rest of the systems of the robot and made cost functions from it. Okay, and that'll bear on in 1 second. So the other interesting part of this problem is that humans are actually quite good at it. So a human can drive the robot from point A to point B quite successfully. And they can either do it from looking at the robot's own sensors or driving by remote control. Okay, both of these are effective. And we'd really like to take advantage of that. So we take as input some sensor data that describes the world, and we provide as output what we want the robot to do, and we want to learn that from human demonstration. Okay, so one thing I learned when I first started out as a faculty member, and I really learned it from a lot of other faculty members, but particularly Tony Stentz, was that one of the most effective ways to get to structure the behavior of robots is to make their behavior look like the solution to some optimal control problem, right? Particularly if you want directed, kind of long horizon behavior. And you see this again and again. I think if you look in detail at a lot of successful robots, what it looks like is the output is driven by some optimizer, some planner, some optimal controller, something like that. Now, if you think about the learning problem in that context, what you're basically saying is I need to take this sensor data and I need to produce a cost function so that the planner does what I want it to do. And I'm going to define does what I want it to do as mimics human behavior in the same circumstances. If that is the worldview, then the only real question is how do you go from sensor data to cost? That's the basic issue at hand. I think this is one of the core ideas if you want to actually get long-term deliberative intelligent behavior. It's a really old idea. In fact, it goes back in the control theory community to the 60s. Applications were quite different there. And variants of it have been reinvented in both machine learning, but also in econometrics and in operations research. There's lots of different applications of this. One, I'll show you some in a moment, where you're trying not just to be prescriptive about what the robot should do, but predictive about what other people in the environment might do, like, for instance, the grasping task I was showing you before. And it also extends to multi-agent settings. And that's something that I think is still nascent work, but is really exciting. So the very first example of this we ever did, I'm showing here, was have a human drive from point A to point B on an overhead view of the world, right? And ask, if that was the path that a human drove, what should the robot drive from that red dot to that red dot? Okay? And I only showed these because, well, they're very simple, and they're one training examples. So there's literally just that one training example. And it turns out the learner infers that this is what it should do. And the reason it infers this is what it should do is the most parsimonious description it was able to come up with for the initial example was to interpret the world as such. It interprets the thing that you and I reason semantically as a road as low cost, and the thing that low cost is dark, and the things that you and I think of as vegetation as high cost, which I'm showing in white. Now, contra, if you show the human doing this, driving like this, so ducking into the trees and going from location to location, the learner infers that that is the path it should take from point A to point B. And it has a very different interpretation of how the world should be costed. Okay. I'm going to belabor the point for a minute because I want you to understand how this particular algorithm that got used in this robot works, because I think it's kind of interesting. It's a very, very simple algorithm, and it's simple enough that I think it points at kind of a bigger picture. So the simplest version of this algorithm I know is the learning to search approach, where we're going to incrementally build a cost function, okay? So that the robot agrees with the human as to what to do. Okay, and what we're going to do is we're going to build a set of component cost functions, little bits that we add together in an additive model. There's nothing that has to be additive model about this. I think it's the easiest way to think about it, but you can apply this with neural network cost functions, as David Bradley, who's in the audience, did as part of his thesis work. Or you can apply it with decision trees or lots of other learners. But I'm going to give you the kind of additive model approach because I think it's the simplest. So what we're going to do is compute a series of little cost functions that we add together to get the total cost function. Okay? And here's the approach. We start out with some guess of the cost function for the world. And the simplest guess is everything's uniform, right? That's the simplest cost function. If we ask the robot, what would you do to get from point A to point B? It drives in, approximately a straight line. Okay? It's a kind of crude version. Now note, in this particular example I'm showing you, that is not what the human did, right? The human did not drive in a straight line. And you can infer semantically why it did not drive in a straight line, why the human did not drive in a straight line. Okay? So how are we going to fix this? Well, the way we're going to fix this is we're going to make a data set, and that data set looks like, look at the places where the human went, but the planner does not currently intend to go. Not where the robot actually went, but where the planner intends it to go, right? And where the person went, we really ought to lower the cost. We ought to make it more attractive to go to those locations. Where the planner currently wants to go, but the human didn't, well, we should make it more expensive to go to those locations. Okay, and I'm giving you this is actually solving an optimization problem, but I'm giving you the kind of intuition. But you literally form a data set that looks like the places, you're basically building a discriminator, if you will, between where the human trajectories go and the planner wants to go right now. Okay, and now you hand this off to your favorite learning algorithm, and it returns a classifier, which outputs either +1 or -1, right, or anything in between. And that becomes a piece of your cost function, and you add it in with some weight. And you should think of that weight as like a step size. Okay, now that didn't work, because now we're running into a rock, right? That's not great. So when in doubt, iterate. So what we're going to do is, again, create a data set, which looks like, again, a classifier is trying to differentiate between where the planner wants to go and where the human actually drove. Okay, and we're going to classify those into +1 and -1, and then we're going to add a little bit of the resulting classifier to our cost function. Okay, so this might remind you of some things, which I think is particularly interesting. So a way to think about this is that it's a two-player game where one player is the optimizer or planner or reinforcement learning algorithm, okay? And it's always trying to find the optimal policy given the current cost in the world. The other player is a cost function, and it's trying to tell the difference between the human, the expert demonstration, and what the planner wants to do right now. And this may remind you a lot of things like energy-based models or generative adversarial networks. And this is a point that was made very nicely by both Chelsea Finn and co-authors and Jonathan Ho and co-authors. What you're basically doing is training, in this process I just described, is you're training a discriminator that's actually trying to tell the difference between trajectories from the learner, from the planner itself, and trajectories from the expert demonstration. So if you think about this, I would describe this as dual ascent, right? And by dual, I mean, I think of the trajectory generation as the primal activity and the cost function as the dual activity. So I'm going to call it dual ascent. What we're doing is, at every step, we are finding the optimal generator for a fixed discriminator and then making small changes in the discriminator, right? Or to phrase it in inverse optimal control, we're finding the optimal plan or the optimal policy and slowly changing the cost function. So concretely, what's that look like? This is an example from David Silver's thesis work. It's one of 50 examples that have been driven. And what you're seeing is slowly the cost function is being interpreted again on an overhead imagery description of the world so that the path driven by the human is matched by the planning algorithm itself. Okay, and this particular example, as I said, there's about 50 data examples that were collected driving around, human going from point A to point B, running the algorithm, or rather a slight variant of the algorithm I just described. So you can apply this to all kinds of problems. One of my favorite was Nathan Ratliff and Matt Zucker's thesis work. They looked at the problem of, I would describe it as rock climbing locomotion. So very careful deliberative placement of feet to be able to cross terrains that are particularly difficult. It turns out humans can actually provide expert demonstrations of where the feet should go, albeit quite slowly. And the result is you can run a footstep planner that figures out where to place feet to be able to go across different terrains. Okay. And the basic algorithm here is essentially the same. And you get pictures that look like this, which is some interpretation of what the cost of placing a foot at each location is. So as I said, in the example of the brain-computer interface, you can use this to forecast intentions as well. And so Chris Catani and Brian Ziebart, in some of their work, looked at how you can forecast the activities of, for instance, pedestrians, right? You can look at either conditioned on goal or not conditioned on goal. I'm showing an example here, conditioned on goal. Understanding what are the semantics of the world, and given the semantics of the world, where do humans find it expensive to go? Humans find it fairly expensive to climb over cars. They could, but they're unlikely to do so under most circumstances. And given a cost function interpretation of the world like this, you can predict what are their likely trajectories out in the future, okay? Even quite far out in the future. And so what's the summary of this? Why would I care? Well, I think it's interesting to think of inverse optimal control as a game. And as I said, as pointed out by authors recently, closely connected to some techniques that are very exciting in machine learning right now. And in fact, you can write down directly for some of these problems, this is assuming cost functions are closed under linearity right here, that, for instance, the maxent formulation of the problem, which is the example I just showed you, can be written down in this mini-max form. And it turns out lots of alternate forms have similar interpretations. Once you have that viewpoint, it suggests lots of other approaches. For instance, primal ascent, right? So what is primal ascent? What I'm doing in primal ascent is I'm slowly changing the optimal policy. I'm moving the trajectory slowly, and I'm immediately updating the cost function to my best guess of the cost function, right? So I've in fact flipped the min and the max, okay? It's also very tempting, albeit difficult, to do simultaneous play, where you try to adapt them both simultaneously. And now we run into problems, because it's very hard to get stable algorithms that have this property. And the reason it's hard to get stable algorithms that have this property is you're playing a game. It's not an optimization problem, right? And one has to remember that. So most of the algorithms I've worked on are dual ascent. Primal ascent is another interesting technique for this. And being able to do both at once is, I think, a very interesting view. Okay, another example that I don't think people, maybe they do, don't think people think of very often as a game, but I tend to view as a game. So I would argue that many of the most successful uses of reinforcement learning in robotics rely upon a model-based approach. So they have some model of the environment, and then they optimize that model of the environment. From a RL point of view, I think that's true. But if you take a broader point of view and think about engineered systems as a whole, right, then if I include in that what we call system identification plus optimal control, I would say that that is how we build robots. Right? We do some kind of system identification, and we do some kind of optimal control on top of it. So I think system identification and optimal control and model-based RL are effectively the same problem, just sort of phrased differently. Okay, so examples of this, near and dear to my heart, from my thesis work is helicopter control. And I'm going to show examples from Peter and Adam's simulator on the beautiful work they did on acrobatic helicopter control. Okay. So the textbook's approach to optimal control is you do system identification first, and then you do optimal control. Okay? It's quite literally the textbook. If you look at Leonard Thiong's book, he tells you this is what you do. In practice, by the way, this is not actually what engineers do, which is a sure sign that something's wrong. We'll see what's wrong in a second. So what do? You have some exploration policy that collects data. Okay? And there's many ways that we can come up with exploration policies. And in fact, that's a subject of its own study. We collect data under that exploration policy. We observe a whole series of transitions of the dynamics of the system, the controls input, as well as the system transitioning from state to state. We fit a model. So we're now firmly in the statistical learning area. We're going to fit a model of what's going to happen in dynamics. We take that model, we apply that model in combination with a cost function, and we synthesize a policy. Right? We synthesize an optimal controller, and then we execute that. Right? And that is the kind of textbook how I build a control system, right? An optimal controller. It sounds good in theory. And in realizable cases, it can actually work. This is an example. It's all in simulation, which you would think would be the best possible case. So there's some expert demonstration of a particular behavior. In this case, it's a nose-in funnel, which is a task which is actually quite easy for computers and quite hard for people because the frame change to do. So this is optimal control synthesis on top of learning with some 35,000 examples of training data. And it was sort of catastrophic. It's not quite as catastrophic as that because even the simulator becomes wrong at some part of the regime, and so a real helicopter wouldn't behave like that. But it didn't work. And so the question is, why didn't it work? Right? And it's actually quite easy to answer that. So what happens is we learn a model from observation, which is good in essentially the data support of how we collected that data. Okay? And in fact, the more densely we collected the data in some area, the more likely the model is to be good in that area. Or perhaps we just failed to fit the model. But assume that we were able to successfully do a good job of getting a low training error or even low validation error model. Okay? Then what happens is the planner or the optimal controller ends up choosing controls that reach states that actually were not reached under the exploration distribution. Okay, and so we end up in a case which is super unattractive from a supervised learning point of view, where we've achieved low training error, low validation error, we have an optimal controller, maybe a perfectly optimal controller, and yet we have terrible test performance, right? Not me. So the fundamental issue here is that I think it's actually more useful to think as model-based reinforcement learning as actually a game where there's two players. One player is effectively learning the model, and the other player, the optimizer or optimal control synthesis algorithm, is desperately trying to exploit that model. Right? And so anywhere the model learner makes an error which is optimistic, so it thinks something better is going to happen than is actually going to happen, the optimal control synthesis algorithm, the RL part, will exploit that. Right? And it will do things that are not physical. Okay? So Chris Atkinson used to tell me years ago that the best way to debug your simulator was to run an optimal control algorithm on it because it would find the bugs in your simulator, right? It would exploit anything that you had done wrong in your simulation. Okay? And for those of you who've seen the DARPA virtual challenge, I think the key lesson from that was not that the simulation could achieve those tasks, but rather you could exploit the simulator. So optimizers in RL actually exploit any inaccuracy in learning. So how do we combat this problem? Well, here's a way. There are other ways too that I'll mention at the end. One is again, this is going to end up being a dual ascent algorithm. This is called Dagger for system identification, and I'll describe it to you. What you basically do is you collect data under a mixture of two distributions. One, distributions of data where you think is close to what a good policy does, and two, under the current policy. So whatever your current policy is, you execute it and collect data. Just as before, you collect transitions of how you think the dynamics of the world work from observing that data. You aggregate that together with all previous transitions that you see, and you fit a model. Okay. You hand that off to an optimal control solver, and then you execute a new policy. Okay. And then you iterate this loop. It's very simple, right? Again, it is, in a sense, you can think of this as, maybe you want to think about this as primal ascent, because what we're always doing is finding the optimal controller given our current fit of the model. And then we're slowly changing our fit of the model over time. Okay? So if we apply this kind of idea and you iterate this loop enough times, where enough is computed from theory, you get better performance guarantees. If you can actually build a low training error model, and you run an algorithm which has the no regret property, which we'll talk about in a minute, but for the time being, just think of that as sufficiently stable, and you run a good optimal controller, you will actually get good test performance. So looking at that example we just looked at before, this is the same number of training examples. The only difference is how the training examples were generated. Right? So in this case, they were generated by samples of the expert demonstration, always, but also mixed in the current best guess of how to control the helicopter. Okay? And good things happen. And I could show you plots of good things happen, but suffice it to say, good things happen. So these kind of issues, in my mind, are pretty foundational to how we think about machine learning, because we've moved from a world in which we're the classic supervised learning setting, where we have a fixed data set, and we're trying to optimize some performance, to where we're actually playing a game, and the game is interactive. One of the strategies that I find most profitable to think about this is what's called no-regret learning. And no-regret learning is, I think, familiar to a lot of people, but it grew up sort of in a different community than statistical learning, because it grew up in an adversarial framework. It turns out it's very convenient because we effectively are in an adversarial framework. And so the idea here is you have a learner that, for instance, outputs a policy, and then there's an adversary which responds to that policy and gives back a new mini batch of examples. That mini batch of examples is IID data from within the batch, but across iterations of the algorithm, the adversary could be trying very hard to break you, in the same way that, for instance, the optimal control synthesis algorithm is deliberately trying to exploit any errors you've made in modeling. Okay. How to think about no regret if you're not familiar with this, the way I think about it is the following two things are sufficient to have what's called the no regret property, which is if you have an algorithm which is asymptotically optimal, what you might call statistically consistent, so if you give it kind of an infinitely large batch of data, it will give you the right answer, and it's sufficiently stable in the sense that if you make vanishingly small perturbations to its data set, it doesn't radically change the output. Those two properties actually guarantee no regret. There are no regret algorithms that don't have those two properties, but all the ones I know of in practice do. And these are not exotic algorithms. So these are things like gradient descent on convex loss functions, rather sequences of adversarially chosen convex loss functions. Follow the regularized leader, where you collect data over time, which is the example I was describing with aggregation. So these are not exotic algorithms. They're things that we're very familiar with, just being used in a game theoretic framework. Things like Newton's method have this property too, or variants of Newton's method have this property. So if you combine these two properties, you get no regret. And in fact, for the algorithms I just described for this kind of model-based RL, you can use any no-regret algorithm in the inner loop. You don't actually have to aggregate this data together. You can just slowly change the model over time, for instance, using a gradient descent method, even though the data is not IID at all, right? And you are essentially solving this primal ascent problem. Okay. So again, I think why do I think the view of games is useful? Again, it suggests different algorithms and different approaches that you might try. So again, whether you call it primal or dual depends on whether you consider the model or the trajectories themselves as the thing that matters, as the primal variables. But one version of this is the approach I just described, the data set aggregation for system identification, where we're stably optimizing the model, meaning we're making slow changes to our view of how the world works, while in the inner loop, we're finding the optimal policy for that slowly changing thing. Okay? And that's one version. You can also look at the dual of this. And I'm reminded of Sergey Levine's work as an example of which something almost like the primal ascent version of this algorithm, where we're stably optimizing the policy, we're slowly changing the policy, while we're finding the best fit model for that current policy. And again, you're very tempted to try both at once, to try to slowly change the policy and slowly change the model. And again, you have to be careful because we're in a game theoretic setting, not in an optimization setting. So we have to be very careful that we're trying to find a saddle point. We're not trying to find an optimum. Okay. It turns out that this problem I described even arises if you don't have a model, which is, I think, a little surprising. But there's a kind of almost a folk literature on model-free reinforcement learning, which is the series of hacks to make it work. And they're often kind of buried in papers, and you'll ask people, well, why did you do that? And the answer is, if I didn't do that, it was totally unstable, right? And similarly, there's a whole series of negative results or counterexamples to approximate policy iteration in the literature. And so we're sort of in a difficult spot, and I want to point out why this actually happens. So thinking a little bit about how does policy iteration work, and this is again a caricature example of policy iteration with the same cartoonish figures. So how do we do policy iteration? Well, we have some way of generating data. I'm going to call it an exploration distribution. Sometimes it's called a baseline distribution that we generate samples from. It's very closely connected, as kind of foreshadow discussion later, with the idea of curriculum learning, where we have some way of sampling states which we hope is close to what a good policy spends time in. We sample states. From each of those sampled states, we try the actions that are available to us. For each of those actions, we measure the cost to go. What's the total cost along the trajectory that results from simulating forward the current policy? And then we get a data set, which looks like, here's an explored state. Here is a cost to go for each possible action. And then we hand it off to a cost-sensitive classifier. And the cost-sensitive classifier's job is to say, if I'm in this particular state, what's the best control I can pick that will minimize the cost function? Okay? It's usually not phrased this way. This phrasing as learning a cost-sensitive classifier was developed by a number of people, including Logodakis and Parr and Alan Fern and some of his co-authors. Most people think about it as, well, I'm going to learn a Q function, and then I'm going to do argmax over that Q function. Okay, but that's actually just a special case of learning a cost-sensitive classifier. That's one strategy one can apply to learning a cost-sensitive classifier, but you can also use weighted losses, for instance, and put them into a decision tree if you like. Okay, so if you run this loop, and so this loop looks like do that, and then try it again, right, and iterate in this loop. If you do that, sometimes it works. Sometimes it does things like that, where the behavior goes up and then down. It's very common to see it oscillate. So you get a policy, and then it flips to a different policy, and then it flips back to the first policy, right? And it goes back and forth. Now, what's interesting is non-approximate policy iteration, like exact policy iteration, does not have this behavior, right? It monotonically improves performance as you go. So what's going on? What causes this failure of approximate policy iteration? Okay, now I'm going to, for want of a whiteboard, I made my best impression of a whiteboard picture. Okay. The bad news is this cartoonish picture may be a little bit hard to go through, so I'll go through slowly. This blue line in the bottom, in your head you're thinking, these are the states of the world. So this is like a 1D state space that describes the world. Okay. On the y-axis, I'm thinking about either value or probability density. In this particular case, I'm showing value. So this is the actual value function that for this particular policy. Okay. Now, of course, I don't get to see that value function. What I actually get to see is I sample states, and then I execute the policy, and I see samples, right, of the cost to go, of the total value. Okay, and I sample from some distribution. So perhaps I sample from the distribution, as in typical approximate policy iteration, of the current policy. And it generates samples according to that distribution. Okay, so some little bump in space. All right, given that distribution, I hand it off to my favorite regression algorithm, and it fits an approximate value function. Is that a good approximate value function? Okay, yes, because its expected error under that sampling distribution is actually not so bad, right? There's some small error in the areas it spends time, but it's not terrible, okay? But the answer is also no, because its worst case error, its L infinity norm error, is enormous, right? But we can't control the L infinity norm error. We don't even get samples in the places over to the left where the errors are high. Okay? So it turns out policy iterations guarantees are all driven by the worst case error of the function approximator. Okay? And the reason is actually quite straightforward to understand, is because after we evaluate the policy, which is what we're doing when we get that red curve of the approximate value function, what do we try to do? We try to improve the policy. How do we improve the policy? We try to choose actions that will drive us to states where the value looks good, where the value looks high. Okay? Well, unfortunately, in that area where we have very few samples, we misestimated, and in fact, we overestimated the value by a fair amount. So what happens? What does the algorithm do at the next step? it jumps over here. And this step that I called a policy improvement step actually became a policy unimprovement step, right? So it thinks that it's going to improve the value of the policy, but actually it has jumped far enough in the space of distributions that it's actually doing worse than the policy we had before. Okay, so again, a way to think about this is that there's a two-player game again going on between an approximate policy iteration. So one player is the policy optimizer, and the policy optimizer is effectively computing distributions over state actions. It's figuring out what the optimal policy is given the current estimates of the value, the sort of value estimation, the cost to go of state actions. And these players are going back and forth. And again, the policy optimizer will always attempt to exploit any errors that are, at least any optimistic errors, that are made by the value estimator. Okay? And again, this connects to research related to, for instance, GANs. Okay, so why is this a useful point of view? Well, it again suggests multiple strategies one might think about. So one strategy, which I think is maybe the most common, is that you'll slowly adjust the policy while fitting the best Q function you can. So I would call this the primal ascent version, right? So you're slowly changing the policy. You deliberately, conservatively change the policy while constantly refitting the Q function all along the way. Okay, so the inner loop is fit the Q function like mad, and the outer loop is slowly change the policy. And it turns out lots of things have this flavor. So one I'll talk about briefly, no regret policy iteration has this property. Conservative policy iteration very explicitly is designed to do exactly this. That's its mental model. If you look at old algorithms like the natural and covariant gradients, they're explicitly designed to do this. They're explicitly designed to control the region in the change in distribution over trajectories. So they're trying to slowly change the distribution over trajectories while maximizing the improvement they get while they make that change slowly. Okay? So they're of this, of the kind of primal. You can also think about the dual version. The dual version is I'm going to stably, meaning slowly, adjust the value estimation with the best response policy. So the inner loop is find the best policy, find the best policy, find the best policy, and the outer loop is slowly change the value, the value estimator. The interesting thing is that duality is exactly the duality between policy iteration and value iteration. Right? So in one, we're really learning a value function. In the other, we're really learning a policy. But they're very similar algorithms. It's just a matter of which one you're trying to move fast. Okay? And again, one is very tempted to adjust both at the same time. You're adjusting the policy as you're adjusting the value function. And again, you have to be very careful because you're trying to find effectively a saddle point, not effectively an optimum between the two. Okay? And there are algorithms that have been invented that have this property. So Konda and Tsitsiklis did some work on multi-timescale actor-critic algorithms. And basically what they're doing here is saying, well, I don't actually have to solve the inner loop to completion. I just have to change the outer loop of my min-max to run much slower than the inner loop. And as long as I keep the timescales fairly separated, I'll be able to find an equilibrium. Okay? Which, by the way, is one of the interesting general strategies for finding equilibrium in all of these games. Right? So one of the points of this is we see the same things again and again. So let me give you what the no regret version would suggest, which is very simple. It says what one ought to do, maybe, is the loop I just described where we collect cost to go of the current policy in the explored state actions under both the current policy and some exploration distribution. And again, we get the same data, which looks like a state, and the cost to go for each action. You could run this in a bandit way. That would be fine as well. We aggregate that together with all the data, or again, we do something which is going to stably change the policy. We hand that aggregate data off to a cost-sensitive classifier, and then we go iterate the loop again. Okay? The key difference here is we're changing things slowly. We're not replacing the data set with a new data set. We're aggregating the data sets together, or running an algorithm that attempts to do well over time on that aggregate data set. Okay. So you can actually prove things about this family of algorithms, whether it's CPI or no regret policy iteration. And they say things like, if you have a good exploration distribution, which again in your head think good curriculum, and a no regret algorithm, an algorithm which is stable, you'll get near optimal performance relative to that exploration distribution. Okay? For the general RL under function approximation, this is the best I know, but it's still really weak, which is unfortunate, but It's the best we can do. It implies certain things, like if you have a good curriculum, you should do very well. If you have a good, for instance, if you see expert demonstrations of states, you should be able to do very well. If the MDP is very smooth, for instance, very stochastic, you should be able to do well. And you get the same bound as some other existing algorithms like conservative policy iteration, policy search by dynamic programming, but you can be much more efficient in the time horizon with this kind of approach. Okay, conclusion. I think many of the problems in robot learning are best thought of not in the framework of statistical learning or not in the framework of finding an optimum, but rather in the framework of finding an approximate equilibrium. And that includes problems like shared autonomy, problems like self-driving, where you're interacting, where you're clearly doing something game theoretic and interacting with others in the environment. But it also includes problems like inverse optimal control, generative adversarial networks, energy-based models, multi-agent interaction in general. I think it's fair to say that there's been insufficient progress on algorithms that actually stably and reliably will find these equilibrium, right? Often because the problem has been viewed as an optimization problem at heart instead of an equilibrium finding algorithm. And the nice part about thinking of these in a unified framework as you're finding equilibrium is it allows us to transfer algorithms between different domains because they're all solving very similar kinds of problems. I'd like to thank a whole variety of people, and I just managed to write down a number of the key players and the supporters of this research. That's all I got.
All right, thanks, Drew. So I think we have time for a few questions for the speaker.
Nice talk. I mean, I missed the first part of your talk, so you may have answered this already. How does this work compares or places itself with respect to standard adaptive control, right? Where you have a model, where you have a control system based on a model, and at the same time you update the model, and you have an overall Lyapunov function which shows that you always converge to the task, so which kind of gets away from the problem you might have not explored the right space and things like that.
It's certainly closely connected. I guess I tend to think of adaptive control and reinforcement learning as essentially the same problem, just in different guises. Most of the work in adaptive control typically makes a pretty strong, from a theoretical point of view, makes a pretty strong realizability assumption that the data actually comes from, rather the data I'm seeing actually comes from my model class, and it's generally fairly hard to prove bounds that are independent of realizability. My own particular experience has been that it's actually hard to get many of the adaptive control algorithms to work stably as well, but clearly many people have had great results with them. So these are, I would say RL and adaptive control are in some sense the same problem.
But so in RL, is very equivalent of the global Lyapunov function you find in adaptive control?
Sorry, say it again?
In RL, is very equivalent of a global Lyapunov function that you...
Well, in some sense, the value function is the Lyapunov function.
Yeah,
right?
but that, as you mentioned yourself, it doesn't show that you converge necessarily to the task, right? Because you might not have explored the right thing and so on.
Yeah, right. And so, again, if you make very strong realizability assumptions, like the data actually comes from the model, then you really can identify the model. So for instance, if we looked at the model-based reinforcement learning example I gave of the helicopter flying, right? If the system really were a linear system that we were driving around, it actually doesn't matter how I collect data, right? That's not quite true. I need to explore all the modes of the particular system, but it doesn't really matter how I collect data. I just have to explore all the modes, and as long as I hit every mode, get enough data, I will learn the model, and I'll be fine, and I'll get my optimal controller. In practice, that's not what happens because our models are always approximate, right? And it does matter the distribution that I collect my data from. It's not as if just hitting every mode will actually get me success at the problem. So data distributions, I would argue, actually matter in practice.
We can talk.
Okay, thank you for the talk. In case of the prosthetic arm control,
yes.
So is there any possibility of the neural feedback? I might misheard some point. You have some BMI interface and capture some signal from the subject.
Yes.
So the subject can observe its own signal, some neural feedback.
Oh. Okay, so let me make absolutely clear. I have zero expertise in brain-computer interfaces. None at all. I don't know whether or not folks have done that or not. It is absolutely true that the training procedure for this, they actually fit this linear regression model. And the way they do it kind of involves a neural feedback process. They've also gone way above and beyond. My understanding is the current state of the art is they're actually able to feedback forces from the manipulator back into the brain, which is truly amazing, so that you can feel what the robot arm feels, another kind of feedback. But again, this is not my area of expertise.
Okay.
I find it magical.
Okay.
Hi, for the example with the helicopter, you have one example where you have an expert that's performing, I imagine, with a real helicopter, and you've collected data from it.
That's not a real helicopter,
Not a real
purely a simulator.
Okay, so
Thank
not
you
a real
wherever he
helicopter.
is.
So seeing this is being optimized within simulation, it feels like you have a third player. Is that simulators have artifacts, they have inaccuracies,
Oh,
and
yeah.
so
Yep.
you're improving the model for your controller, but you're not necessarily improving the model of your physics at the same time.
No, that's absolutely true. I was in this case treating the simulator as if it was the real world. The point being, the prescription I'm suggesting, which by the way is the prescription I think any engineer worth their salt would do in practice, is that it's very useful to go collect a bunch of data under some expiration distribution in the real world, not in the simulator necessarily. Do your best job for finding a policy for that model. Start running that policy. When things look like they're getting off the rails, stop, right? And keep doing that, collecting the data together, aggregating the data, building a better and better model, right? And at some point you will either exhaust the ability of your learner to be able to fit the data, which could happen. There may not be any model that can fit it, or you'll build a good policy. One of those two things will happen. You're absolutely right. If you wanted to transfer this to the real world, you would have yet a different problem, right? Which is the simulator. The simulator is not perfect.
The thing is that you can't really iterate on your model of the real world, because
You absolutely
then
can.
you break a lot of helicopters.
You absolutely can, but you have to take over, right? So that is often, in fact, how such models are built, is that you actually go try them, and then when things go awry, you have to take over.
Can you opine on if you add an artifact or noise to simulation in a way to push it toward what you might experience in the real world, does that improve this kind of learning?
Yeah, so well, I can tell you my experience. My experience when I built helicopter controllers was I found it very useful to keep distributions over potential models for the helicopter and then optimize the performance against the distribution rather than a single particular model. I found that was much more robust than transferring to the real world, right? So that you had a controller that was successful at controlling many different helicopters that were kind of close to each other. And I found that pretty critical to get things to work. The logic at the time was a kind of Bayesian view that you hadn't collapsed your uncertainty around the model, but it's even true if you've actually collapsed your uncertainty. It's still nice to keep around distribution over models.
Thank you. I think we all learned a lot.
All right, so I think we have time for maybe 2 more quick questions.
Hi, thank you for your great talk. So the examples that you were showing, they seem to be fairly smooth dynamical systems that were moving. The helicopter was example, and probably the car is a fairly smooth system. So
If things go well.
If things go well. So how do you think you would apply these things to the systems that have hybrid dynamics? So there would be an additional issue of understanding in which kind of mode you are in. So you would start to have this kind of growth of uncertainty in where you are. So what model do you even identify? Can you evaluate all the possible models that you should be identifying? So how do you think you would address those kinds of problems?
I guess I don't know how to answer that. I certainly agree that any problem, for instance, like manipulation, it's very hard to come up with, to learn models of these tasks. I don't think it changes anything in a sense. I think the same lessons apply, right? I think you're still in a world where you're trying to find effectively equilibrium. Just the modeling problem is harder, right? In fact, it may be so hard that sometimes it's not worth doing, right? You may hit cases where it's actually worth doing model-free RL. Right? Your mileage may vary. If you can build a model, you probably should.
Cool, thanks.
Thanks for the talk. It's really interesting, and I completely agree with you about the interaction between samples and control. But I do want to mention, for the record, that exact same maneuver you showed was done on in-flight with an adaptive controller, model reference adaptive controller.
Oh, I could believe it.
Eric Johnson and myself, and I mean,
Yeah, yeah.
so I agree with you that in general you can view reinforcement learning and adaptive control as being parallel. There's a paper that Sutton wrote, but I think there's a lot of work on these safe and stable adaptive controllers, including some that John has done.
There certainly is beautiful work in the control theory field.
Thank you.
All right, let's thank the speaker again.